then the thing we're gonna prove is a to the t equals e, if and only if, there's this a q in the integers such that t equals nq. Now, the reason it's so important that we do this proof is because this proof, this proof area serves as a template for the kinds of proof writing things you're going to see in other places. So you want to kind of pick up these techniques and how to write them and the notation and how they're structured, that kind of stuff. So, if and only if proofs, as you know, you have to go left to right and right to left. We're going to do right to left first because that's the straightforward way in my opinion. So we're going to suppose t equals n times q. Do we start with our hypothesis, our hypothesis? No, we start with the conclusion. So we're going to start with a to the t. That's our conclusion because we're going this way. A to the t, then we use the hypothesis, that's a to the nq, and I'm just going to do a shorthand here. That's equal to a to the n to the q. Why is that true? Laws of exponents that we proved, that you're going to prove some of them in the homework. Okay? Oh, and you all found the drop box, right? This is e to the q. Why is that? Hypothesis, order of a is n. And this is e, that's just definition of e. Okay, done. So if I walk in and I say, put your thinking cap on, and then the first thing we do is this easy, you know the second way is not that easy. Okay, any questions? So in order proofs, you are almost always going to show that the power of something is e, by hook or by crook, somewhere in that proof. So we've done that for this proof. We're going in the other way. We're saying a to the t equals e implies t equals nq. Okay, so this is our hypothesis, this is our conclusion. Okay. So, we know order of a is n, and a to the t equals e. We need to find an expression for t. Okay, so we're starting with t. T and n are fixed. Okay, we're given those. So we're going to use the division algorithm. There are two reasons for using the division algorithm. It's in the chapter that we're reading on. So they wouldn't put it in that chapter if we're going to use it. And that now becomes, okay, in your toolkit of proofwriting, you see all these niches and tools, and like it looks like those red tool bit kits that fit on the back of the truck, and you see wrenches and screwdrivers and hammers, and you've got the division algorithm in there with the hammer, okay? So when you're writing proofs, you may have, you know, like you might be a carpenter, you might be a plumber. You got a toolkit for the carpentry work, and you got a toolkit for the plumbing work. So you want to think of all these techniques and consciously say, this is a technique I use. If I'm given two integers, I might wanna use the division algorithm. That becomes your go-to, one of your go-to things to check. Is the division algorithm gonna help me? Just like if you've got a triangle, you might wanna use Pythagorean theorem. That's your first thought, I might wanna use Pythagorean theorem. Your second thought might be, I need to use similar triangles. Okay, so there exists Q and R, and I try to stick with Q and R for quotient and remainder, such that T equals NQ plus R, and R is greater than or equal to 0, less than N. Okay? So now we use our hypothesis. So E equals A to the T equals E to the NQ plus R. Right? Substitution from the division algorithm equals A to the NQ, A to the R. Law of exponents. What else were you gonna do? Can't think of anything else to do, so do that. Equals, just got through doing it up here, A to the N to the Q, A to the R, law of exponents, equals E to the Q, A to the R, order of A, equals A to the R, property of E. So now we got A to the R equals E, and R is less than T. So by definition of order and our description of R, what does R have to be? 0. So I need to write that part down, okay? Okay. Oops, I knew it was gonna do that. Okay. We now know A to the R equals E. N is greater than R is greater than or equal to 0, and the order of A is N. Those three things together logically tell us that R has to be 0. Since N is the least positive, 0 is not positive, integer, such that A to the N equals E. We must have R equals 0. So T is Qn, because we zeroed out the remainder. Okay? And that's what we wanted to know. So this is not that bad. It's a little convoluted. It's more than unusually unknown to you. It's not something you're familiar with, except for you guys that do number theory. What?
Why did we switch AT to EN? Is it because AT equals E?
Yeah. By our hypothesis, AT equals E, and I just wrote it in the other order,
Okay.
so that I could string it to the right.
Okay.
Okay? Okay, same. Okay, so I'm gonna look on C3 in this chapter. You should know this proof of theorem 5. This is like a benchmark proof. So even though it doesn't have a name, you should know the proof. And by the way, while I think of it, if the theorem has a name, you should be able to state it. So I would feel free to ask Cayley's theorem as a definition. So what was Cayley's theorem?
A group is always isomorphic to a group of permutations.
Yeah. Did everybody get that? Okay. And that's pretty much a good rule of thumb, because as you get in further deeper into mathematics, people are gonna throw out so-and-so's conjecture, or Fermat's last theorem, or Cayley's theorem, and they're gonna think you're an educated math person, you know it by name. There aren't that many of them. Math people don't tend to name their theorems after people. So. Okay, C3, in the homework. This is my illustrative, theorem. And we're gonna do something a little bit different here. So I did this 2 ways. We're gonna do both ways, and then you're gonna critique them. Not in the sense of, oh, this is wrong or right, just, I like this, I don't like that. This is easier to understand, that's harder to understand. And that's all personal opinion, so, you know, everybody's entitled. Okay, C3 says, so you're gonna work on A. B is nice and fun and simple. B, it's pleasant. Math people love B. C3 says if A to the K equals E and K is odd, then the order of A is odd. So let's write that down. Now this is a little weird. I mean, to me, this is a little weird. For example, if you're in, let's do integers mod 7. And, no, let's do 9. And the order of 12 is 4, right? Now how do I get the order of 12 is 4? Well, 12 is 3 times 4. So I got a 3, and I'm multiplying 12 times 12, etc. I got a 3 from 3 divides 12, so there's 2 3s. And I need to get, it is 2.
3?
Yeah, it's 2. Thank you.
3,
No, it's not 2.
it's 3.
0 and 12.
It's 36.
3. Yeah, I've got 1 3. Wait a minute. 12 times 12 is 144.
It's,
You're doing 12
it's
times
addition
12.
or,
You're right.
Yeah.
I told you, I'm having too many Mondays. I've got one 3, and I need 3 3s, so I've got to add it up 2 more times to get all 3 of the, to get all of the 3s I need. Yeah.
Okay.
Yeah, I'm just trying to figure out why my brain is not getting on all cylinders. Anyway, what this is saying is, if, you're adding up and it requires an odd number, then the order, nothing higher. If n is odd, nothing higher, nothing higher can ever be even. If you get one odd power, then everything that comes before it had to be odd. Or the lowest power had to be odd. It's kind of weird. It's like if you're looking at this, you're looking at A, and like you said, we're doing pluses. And somewhere out here, you get E. Then that E out here, if you weren't paying attention back here, that E out here told you that the first time you got E had to be odd also. That's just kind of weird, that it's kind of like, the opposite of predicting the future. If you see the future, you can kind of go back and say something that happened in the past. I just find that odd, pun intended. So anyway, let's do the proof. That was not as helpful as I thought it might be. Okay, suppose a to the k, here's my proof one. Suppose a to the k equals e, and k is odd. From theorem 5, there exists a q and z such that k equals nq, and n is the order of a. So we've got, if you've got a, in the theorem 5, they used a t instead of k. A to a power equals e, then the order of a divides that power. So my one hint or suggestion, you number theory people can thumbs up or thumbs down the suggestion. If the problem says divides, multiplies, is a factor, factors, rewrite something as an equal sign with a multiplication problem and drop the words, use the formula. Your life is so much better, okay? So, now suppose we're trying to prove something about a to the n is odd. Suppose the order of n is even. And that means, right, the order of n is 2 times something, we'll use p. Okay. So now, substituting k equals 2pq. This contradicts k is odd. So k is, so n is even. I mean, n is odd. We supposed n was even. Here's our, there's our supposition that led to a contradiction. So our supposition was wrong. Yeah.
This is like a basic property of odd and even number, like odd times odd is odd and odd times even is even. So for it to be odd, the n has to be odd.
But you gotta get it down to more than just a, I mean, there is a piece missing here. The piece missing is a number can't be both even and odd.
Yeah.
So you would have to prove, or quote that proof, or be convincing. If someone was completely unfamiliar with odd and even, they might need an explanation of that. And you could probably, from your observation, probably shorten it a little bit too if you wanted to, if someone were used to thinking about it that way. But this does not clearly lay out in my mind, so I wrote it another way. This doesn't start with to me, it doesn't really start with the conclusion and then use the hypothesis. It kind of blurs the beginning. So let's write it a different way, and then you look at it and see what you like and how you feel about it.
So for these, we'll probably be using like the form of even and odd numbers a lot, like 2k and 2k plus 1.
Yeah.
For even or odd.
Yeah, and that's what you use to prove that a number
And
can
we
be
want to
both
say
even
it,
and odd.
we want to state it here.
Okay, so remember our rule of thumb. Our rule of thumb is we're talking to other people in the room who've done the same thing you've done except this one problem. So if you know about even and odd and 2k plus 1 and you want to use all that, do it. If you want to use something a little bit different, do that. You don't have to go back and prove all of number theory. Yeah, nice of me, isn't it? Okay, suppose k is odd. And a to the k equals e. We proof by contradiction. So we start by supposing order of A is even. So there exists a P in the integers such that N equals 2P. That's your definition of even. Okay. By part of the definition of order, A to 2P equals E. Because the order was N, N is 2P, so A to the 2P equals E. From theorem 5, K, let's back up. There exists Q. Yeah. Q in integers such that, now theorem 5 says random exponent equals order times something. Q is the something. Random exponent K equals the order times something, which is 2PQ from substitution. So K is even. This contradicts the hypothesis. So our assumption that N is even is incorrect. Well, is false. And N is odd. Okay, so which one do you like better? Do you see much difference between them?
Definitely like number 2 better.
Number 2 is my second draft. Hmm? Okay, so why do you like number 2 better, and why do you like number 1 better?
Just my understanding.
Well, yeah, but why? Narrow it down.
I really like number 2. I had a lot of trouble understanding problem, but I understand it now with problem 2. It explains it a little bit more, especially like the contradiction part that kind of forms the whole argument.
And you got fair warning
Yeah.
in advance that you were doing contradiction. That's a nice touch, right? Somebody else weigh in.
I mostly see them the same. Like the only difference I see between them is like the 2 lines are just switched. They just replace each other.
Fair point. They were kind of written down in a different order.
Like the order is just kind of, changed.
I think I like proof 2 better because in the first one you said the order of N is even, but seeing that the order of A is N is even, like we're supposing that in the second one, I think that makes sense to me because in what we're supposed to be proving, we're saying it's odd, and if we're contradicting it, we're saying it's even, so then we go from there. Does that make sense at all?
Yeah, and it's kind of like, okay, so I am giving the reader a preview of where we're going, and I'm being very explicit about what our assumption was. Here, it may be not quite pointed out as well. But they are in a different order, and the different order does make a difference. Okay, Clay?
I like the first one, because not only is it more concise, but I feel like there's a couple keywords there that gives me clues as to what you're trying to do, like now suppose, that kind of implies, now I'm gonna kind of contradict something, see what happens.
This might be like a little nitpicky too. I like number 2 because in number 1, you kind of just invented P on the spot without telling us anything about P. But in number 2, you actually give us a reasoning as to why P should exist and what kind of object it is.
Yeah, I think personally, number 1 skipped a little bit of detail. It kind of let the reader fill in a few more blanks that were laid out a little more specifically in number 2. However, when I was an undergrad, I had a particular professor, and I ended up, in fact, having him more than any other professor. He was an analysis professor. And I gotta tell you, I just didn't think like he thought. When he wrote out, he was a very careful, diligent person, and he would write out proofs, and he thought they were in perfect order. And what I heard was 3, 4, 6, 2, 1, 8, 9, 0, 15. That was the order I was hearing, and I had to go home every night and rewrite his notes in an order that made sense to me. And I had him for 5 classes, and I never did. I was never able to think in the order that he thought. I had to just go back and rewrite it. I just didn't think that way. So, that's to say, this was the first way I thought. So obviously I thought that was a clear way of thinking. Then I thought, I don't think I'm quite obvious enough. I don't think I've done enough justice for my readers. I went through, and it wasn't so much that I wanted the order to change, but I did want to make these definition of P's, point out that we were doing contradiction early instead of just doing it. And that came to this one. And it doesn't matter which one you do or which one I like. There's gonna be some like it, some don't. Every audience is gonna have a different opinion and different division things. And the whole point about writing proofs is you write a proof that hits 85% of people, and then the other 15% have to come ask you questions. That's the whole point. You're not gonna get everybody on one shot, especially the more complicated the math gets. So the idea of anybody being afraid to talk about their math statements and why they did what they did and just looking at you blankly when you ask questions, that's abhorrent. That is not the way math works. Math is a give and take, it's I understand, it's common vocabulary. You have not proven anything unless somebody heard it. It's like the tree falling in the forest and nobody's there to hear it. Did it make a sound? If you write a proof and nobody ever reads it, does it matter? I mean, think of all the stuff that Gauss wrote in the margins of his books and said, I don't have enough time to write it here. All those are gone.
I think it was for Mona.
Hmm?
I think it was for Mona.
Not sure, whichever one. Might have been for mine. All these proofs that people wrote that never got published didn't contribute to anything. It was fun for them, and it meant something for them, and it was good for them. But in terms of advancing mathematics, you have not advanced mathematics unless you really help someone else understand. Math doesn't stand.
So expanding math is just like teaching someone else.
Writing proofs is definitely like teaching somewhere else. Now, from a different perspective, if you're doing applied math and you're solving a problem for an engineer who's going to go out and build a bridge, that's perfectly good, and they may not see your math. The engineer will, but nobody else may, and you still got this bridge to point at. So that's not universally, I'm not saying just doing calculations is wrong or unhelpful. I'm just saying the whole point about writing proofs is communicating, and the whole point about communicating is you may have to say it more than one way, to more than one time. So that's something as proof writers and math majors, you gotta be able to know what ground you stand on. So that when you explain it to someone who conscientiously does not understand, you've got different ways to explain it. And you know why you're true and why it works. Because if you just think it's true and you didn't back check your facts and you're trying to teach someone and they call you, like sometimes you guys say, isn't that supposed to be negative or is that supposed to be even or whatever? I gotta have the confidence in my work to know if you're right and I just did a copy error, or if I screwed something up and didn't think about it. You know, you gotta have that robustness of your reasons, which is one reason why we write reasons. And I thought it was kind of fun to show you a draft 1 and a draft 2, both of which are pretty good. They would stand, you know, either one is fine. I think draft 2 is slightly better than draft 1, but you guys are perfectly welcome to think draft 1 is the better one. It's not a problem. So that was kind of fun, I thought. So C4. I think we'll get through D and then I don't know that we'll get through E. We'll see. Okay, so C4. The order of A. Is the order of BAB inverse. Anybody know what BAB inverse is called? That construct?
Oh, not diagonalization.
Not, almost, starts with a C. CO? Conjugation? Okay, that's a conjugation. BAB inverse is a conjugate of A. That is the underpinnings of the solution to Rubik's Cube. FYI. Rubik's Cube is actually an algebra problem, a group theory problem. And if you want to see that, it's on the internet, you can read up about it. I've always meant to, and I've read parts of it, but I've always gotten behind and couldn't finish it up and haven't done anything with it. So this is called BAB inverse. If you pre and post multiply by an element that's inverse, this is a conjugate. Okay, just a little note there. We want to show that if you conjugate, you don't change the order. Okay, so your A is a group, G is a group, A is in G, B is in G, and this is true for every B in G. Okay, so proof. So this is your classic order proof. And this is your classic proof where they were mean to write it this way, because they led you down a garden path. Your definition of order comes in two parts, right? The exponent gets you to E, and it's the least exponent that gets you to E. So you have to first show that using that number as an exponent yields E, and then that nothing smaller will do the same thing, okay? Which one of those two, we got two numbers written down there, right? If you pull out the equal sign, there are two things there. Which one is it that we're trying to prove about?
Can you repeat the question?
We got two numbers. The order of A and the order of BAB inverse. We're trying to show that those two numbers are equal. Which one is the number you think, how did I say that? Which is the number we're
trying to prove.
Which are we trying to prove? Which of those two numbers are we trying to calculate? Let's say calculate. Yeah, because the order of A, there's nothing there to work with. It is what it is. It's an N. Okay, so trig theorem, trig identities up till today and through calculus take the complicated side and start with it. Cause it's easier to compute when you have more and get it down to less. Starting with less and trying to make more is always harder, cause you're having to invent stuff. Okay, so if two things look about this, if you're trying to do the same kind of thing with two things, start with the one that has more information, which is the BAB inverse. So we want to say, suppose the order of A is n, that's just a notation, and consider BA, B inverse to the n. Okay? And what we're trying to do is we're trying to start the first part of an order proof. And the first part of an order proof says, this exponent gets you to e. So we want that outcome to be e, but we have to calculate it, okay? So what is BAB inverse to the n? It's BAB inverse times BAB inverse times BAB inverse times BAB inverse, and that's done n times. Now, there's two things to say about this. Number one, why did I write it that way? We're gonna use associativity, that's very, very true.
Did you do it so we can see that the B inverse and the B cancel out?
Yeah, I couldn't just do b to the n, a to the n, b to the minus n. Why could I not just do that?
You said you can't do B to the n because it reverses the order.
We don't have a billion, and therefore, remember our proof, our little proof? AB squared equals a squared b squared if and only if g is a billion.
Yeah.
So moving exponents to individual elements is equivalent to assuming a billion. We don't have a billion, so we can't do that. So there are two reasons, you identified them both. There were two reasons to do this. Number one, to see, because we couldn't do it any other way. And number two, because doing this reveals the associative property where the B and the B inverses stack up, and the fact that you use the identity property a whole bunch of times. Okay, so this is B, A, E, A, E, A, E, A, E, A, B inverse. And in here, n times 4A to occur. Is everybody agree? Okay, and we used, as Clay pointed out, we used the associative property. Up here, this is the definition of exponents, of an exponent. If you said anything else, you were wrong. That's the only way to expand that. Okay, so this is B, A to the n, B inverse, definition of exponents, which is B, E, B inverse, definition of order of A is n, which is B, B inverse, definition of identity, which is E, definition of inverse. Yep, okay. So now you're standing on your rocks. Unless you have a copy error or some kind of transmutation, you are solid firm that you got this right. Because you got a reason for every step and you can defend it, okay? And it's not about being defensive, it's about you can explain it and you have total confidence that you aren't lying to somebody. It's more about you being a truth teller than it is about you protecting yourself from an attack. I do not feel that you guys attack me when you ask me a question. And maybe sometimes you are, but I'm gonna ignore that. If you're attacking me, that's your problem. If you're asking me a question, I don't feel attacked. I feel a need to find another way to explain it. But I don't have any trouble worrying about finding that way because I know I'm right. I know I did it right. And so I'll just think about it and find another way to explain it. It's very empowering. Okay, so what we just did was, we said n as an exponent will take BAB inverse back to the identity. That means from theorem 5, the order of BAB inverse divides n, minimally. Right? A to the t equals e, n is t. So for theorem 5, the order of BAB inverse is gonna be n or smaller, put it that way. It could be smaller. Okay. And our proof is that it's not smaller, that it is exactly n. Because this is the n right here. So what we just showed, if you want to say it another way, the order of BAB inverse is less than or equal to n. So now why is there not a smaller number, part 2 of an order proof? Why is there not a smaller number that will get you to E? So your second part of the proof is always going to be a proof by contradiction, usually. 99.2% of the time. Okay?
And what about 0.8%?
There's some proof out there somewhere that needs you to use a different strategy. I'm covering my bets. I try not to say always.
Yeah.
Okay, that's why math majors have such difficult times on true, false, and, multiple choice standardized tests. It's because by the time you get to those, you're used to looking for exceptions to the rule, not the rule. And when people say always, your immediate goal is, okay, let's find something that doesn't work. Yeah.
I only need one.
That's right. Suppose there exists S such that 0 is greater than S is less than N, and B inverse to the S equals E. Okay? So we're trying to say we know N works. How do we know that N is the least integer? So suppose there's a lesser integer. Okay? Then B inverse times B inverse times B inverse S times equals E, right? We said, I think there's a smaller number that gets you back to E. Just like we did before, and we've done this once so we can kind of shorten up the steps a little bit. This means you've got B, A, E, A, E, A, E, A, B inverse is equal to B, A to the S, B inverse is E. So the person we're talking to, they paid attention the first time we did this, we went to the second time faster. Therefore, B, A to the S, B inverse equals E. B, A to the S equals B. A to the S equals E. And S is greater than 0, less than N. This contradicts the definition of the order of A. So N is the least positive integer such that BAB inverse to the N equals E. So the order of BAB inverse is N, which is the order of A. And we're done. Okay? Yeah.
do B A to the S B inverse is equal to B to the A and B inverse, because they're both equal to E.
Sure.
And then do some multiplication to say AS is equal to AN, so S must equal N. Could you do that or no?
S equal AN does not imply S equals N.
No, AS equals AN? Doesn't imply S equals N? No.
Let's look at that. Okay. It does in the real numbers,
No.
but not in integers mod 6.
Oh, that makes sense.
Right?
Okay.
Yeah. No, that's a good thought. That would be a good strategy. It's just that we don't have enough information to use it.
Does that, it doesn't imply that, but does it imply that S is either equal or greater than N?
No, it just implies that the smallest one is possibly the order and the larger one is a bigger power of the same order.
Okay.
Right? In other words, think if the order of A is 3, A cubed, A to the 6th, A to the 9th, A to the 12th, A to the 3n. All of those are equal to E. Because A cubed is E and you just continue to multiply by.
It'll list in the real numbers, because all of those numbers are unique.
Yes, because you don't have any equivalence relation making them indistinguishable, yeah. Clay?
I must say, I think it's very useful to think about something like the unit circle or like roots of unity. Like,
Nice, yeah.
when you're saying, when you're using like the unit circle, you can think of it as like 2 pi, and then like anything smaller, you're not gonna get the multiplication.
And if you wrap a double rack, you're back where you started, so you can get, yeah,
And that's theorem 5 too.
yeah, that's a good thought. Okay? Cool. So there's one thing, stylistic thing, that we can comment on. Once in 100 times, you're gonna see this in a textbook where they put the little brace under it and say n times. There are a lot of mathematicians that really despise doing that. They also don't like what they call this open form, these dots. You know what it means, but they just think that's a bad way to communicate. And they will, an editor for a journal or something will send that back and say, do this differently. The way to do this differently is math induction. That's how you get out, that's how you change an open form into a closed form. And this kind of problem anyway. So how comfortable are you all with that math induction? I mean, you need to be rock solid, really comfortable.
For theory, for
Quite good so far.
Yeah.
Okay, so one thing you wanna do if you wanna kind of brush up your proofwriting skills is rewrite this middle part using math induction, so that you get rid of the dots. You don't have to, it's just a suggestion for expanding a little exercise for expanding your proofwriting. But we've done what we need to do. Okay, so if you look in chapter, there's one more I want to do. Actually, I've got 2 more to do. Okay, I have down to do D2 and F. And then the piece de resistance is E, at least the first 4 parts of E. The kind of the big, powerful ending, okay? So I think what I'm gonna do is let's look at F. I'll save D2. And we can't get through E, it takes too much time, so we're just gonna start something we can't finish. So we're gonna do F1, I'm gonna do D2. So everything from A through D that I haven't done are things y'all can work on. They aren't necessary to do all of them. This is not the trunk line, the main trunk of the tree, this is a limb out here. So we want to spend some time because it's such a good proofwriting style. And it gives you new kinds of examples of ways you write proof and you number theory people. This feels like number theory, doesn't it? So, that's why we're doing it for people who aren't in number theory, because it's a legitimate tree branch. But it doesn't lead to a huge, another branch of algebra. So we did that. We're going to finish up E next time and probably get into chapter 11. And I will throw you a, heads up. Page 113 is the statement, maybe it's the top of 114, I guess. That's the statement of the proof you've got for homework for next week. So if you want to look at that and see, state it yourself from what I said in words, and then go back and check and see what they did here. But they don't prove it here, I don't believe. Okay, so,
Where did you say that?
113, bottom of 113, top of 114. So please do A2 for sure. Play around with all of B, it's fun, especially B5. Take part C pretty seriously. And part D. And I'm gonna do part E. And I'm gonna do this one thing in F, and we're not gonna do any more with F, G, or H. Good, but we're not. Okay, so F, what did F go? Okay, 10F1. For part F, the book is saying, A is an element of order 12 in a group G. And 12 is like one of your best number theory numbers, right? Because it's divisible by 2, it's divisible by 3, 4, 6, 7. Okay, the question on part 1 is find K such that A to the EK equals E, and it's the smallest one. Okay, and he suggests using theorem 5. By theorem 5, 12 divides AEK. Okay. The order of any element divides an exponent that gets you back to E. So I would suggest writing this as a product. And let's use T, such that 8K is 12T. Do you agree? Okay. So, and we're sticking with whole integers, not fractions. 2K equals 3T. So 3 must divide K. Right? Here you look at 2 divides T, but if you look back the other way, 3 divides K. And we're looking for K, so we're focusing in on K. Okay? Lowest or the least positive integer divisible by 3 is 3. So, consider a to the 8 times 3 is a to the 24, which is a to the 12th squared, which is e. So k equals 3. So there are two ways to talk about powers of elements, orders of elements. You can low-tech it. You take a, so you start here. You take a to the 8th, a to the 8th times a to the 8th, a to the 8th times a to the 8th times the a to the 8th. And as soon as you get to e, you stop. That works as long as your numbers aren't too big. You can get it by with a computer program if they're reasonable, like less than 100 million. But anything bigger than that, you're gonna have to use reason instead of brute force. And so you gotta think somewhere like this. Okay? So that's not much of a problem, but I want to point that out. And then we got E. So we'll save D2 and all of E for next time. And we'll do our definition test and call it a day. Any questions? Cyclic groups, blink, you'll miss it, and then we'll spend some quality time on chapter 12. Chapter 12 is partitions generated by equivalence relations. How much did you do that in foundations? Equivalence relations and the partitions that they generate.
Are equivalence relations not partitions?
Yeah.
Okay. That's good. That's good. That gives me a good starting point, a planning point. So you know reflexive, symmetric, and transitive. Okay, cool.